Hello everybody, we're getting ready to do lesson 9.4 part 1 classwork for pre-calculus math today. And for today's classwork lesson 9.4 part 1 parametric equations, we got 16 points in our notebook, so have your notebook guides out, students. And then we got 34 points that will go into your classwork sheet. Have that out as well. Name, date, periods, classroom students, and then onliners and homeschoolers, put your due date here. Today's bell work, students and teachers. Today's bell work, check for symmetry with respect to both axes and to the origin. Then determine whether the function is even, odd, or neither. So for these students, 69 and 70, check for symmetry and then determine whether the function is even, odd, or neither. Give your students about 5-6 minutes, teachers. See you in 5 or 6. Pause your video for 5 or 6 minutes. Okay, welcome back everybody. And for number 69, to check for symmetry, first of all, f of negative x equals f of x, so it is symmetric about the y-axis, and it is an even function because of f of negative x equals f of x. And then for 70 here, we have no symmetry, neither even nor odd, because f of x equals square root of x. X cannot equal, or rather x is greater than or equal to 0. And there is no symmetry. If you know that function, it kind of almost looks like a log function. So it's neither even nor odd. Into our lesson today, page 1, plane curves. Up to this point, you've been representing a graph by a single equation involving two variables such as x and y. In this section, you will study situations in which it is useful to introduce a third variable to represent a curve in the plane. To see the usefulness of this procedure, consider the path of an object that is propelled into the air at an angle of 45 degrees. When the initial velocity of the object is 48 feet per second, it can be shown that the object follows the parabolic path. Okay, so in this situation here, y equals the negative of x squared over 72 plus x. This will be called a rectangular equation. And this would be a situation here where we have a t equals 3 times square root 2 over 4. And then this will be a parabola here. However, this equation does not tell the whole story. Although it does tell you where the object has been, it does not tell you when the object was at a given point on the path. To determine this time, you can introduce a third variable t called a parameter. It is possible to write both x and y as functions of t to obtain the parametric equations. So we need a parameter. It is possible to write both x and y as functions of t to obtain the parametric equation. So we need a general outside parameter of what x and y is up to here. So parametric equation for x, for example, will be x equals 24 times radical 2t. So this would be called a parametric equation. We're going to alter it with this t here. Then y equals negative 16t squared plus 24 multiplied by 2t. This would be a parametric equation for y, parametric equation for x, parametric equation for y with this t here. From this set of equations, you can determine that at time t equals 0, the object is at the point 0, 0. Similarly, at time t equals 1, the object is at the point of here, 24 multiplied radical 2, 24 multiplied by radical 2 minus 16. So things change with time as time moves this function. So curvilinear motion, 2 variables for position, 1 variable at a time. So that would be an example of that, curvilinear motion. And then rectangular equation will be this, and then a parametric would be where you have another variable here, a third variable that determines where the curve will be at a certain time, for example. So it can give us a negative and as well as a positive time, if you can imagine that, where these curves come from and where they're going to go. For this particular motion problem, x and y are continuous functions of t, and the resulting path is a plane curve. Recall that a continuous function is one whose graph can be traced without lifting the pencil from the paper. So these are continuations of what is going on, like with this situation here. It just doesn't stop at, say, the x-axis. It continues. So the continuation is kind of can be expressed by using t as a parameter, general rectangular equation there. So the definition of a plane curve: if f and g are continuous functions of t on an interval I, then the set of ordered pairs f of t and g of t is a plane curve C. The equations are given by x equals f of t and y equals g of t. Our parametric equations for C is a plane curve of C. So, and t is a parameter. So t really determines how far the curve will go in each direction. Graphs of plane curves. One way to sketch a curve represented by a pair of parametric equations is to plot points in the xy plane. Each set of coordinates xy is determined from a value chosen for parameter t. By plotting the resulting points in the order of increasing values of t, you trace the curve in a specific direction. This is called the orientation of the curve. So let's get into an example of this now. Example 1, sketching a plane curve. Sketch a curve given by the parametric equations x equals t squared minus 4, and we have a, talk about parameters, we have a negative t is less than or equal to t is less than or equal to 3, and then describe the orientation of the curve. So here's our parameter right here, t squared minus 4. So using values of t in an interval, the parametric equations yield the points x, y shown in the table here. So here is our curve here. It's not a function, by the way, but using values of t, and then say we have t equals -1 here. This would be like a time here. T would equal -2. So if you just continue this curve and then negative, t doesn't have to be a necessarily time. If you can imagine going into the past, I guess you could. But if you started here and you went like this, and then the curve continued, t equals 2, t equals 3, t equals 4, probably over here somewhere, etc. So it gives you the general orientation of the curve. And then we have a table here. So using values of t in the interval here, parametric equations yield the points x, y shown in the table here. So when t equals -2, which would be here, we have x equals 0, and then y would equal -1. And then when t equals -1, which is here, we have x equals -3, and then y would equal -1/2. And then when t equals 0, which is right here, you have x equals -4, and then y equals 0. T equals 1, which would be about, I guess, here. You would have x equals -3, and then we have y equals +1/2. Then when t equals 2, which is here, you have x equals 0, and then y equals 1. And then when t equals 3, which would be over here, you have x equals 5, and then y equals 3 over 2. By plotting these points in the order of increasing t, you obtain the curve shown. The arrows on the curve indicate its orientation as t increases. So the curve goes in this direction here as t increases. I mean, I guess you could go further back like this too, but in this particular situation with this model is they want you to go forward with it. So here's our curve again. Its orientation as t increases from -2 to 3. So we start here at -2, t equals -2, and then we end up over here at 3. So when a particle moves on this curve, it would start at 0, -1, 0, -1, and then move along the curve to the point of 5 3/2, which is here. Is that right? 5 3/2? Yeah. So that'd be 5 3/2, that'd be there. Okay, let's try one. Consider the parametric equations x equals radical t, and then y equals 2 minus t. A, create a table of x and y values using t equals 0, 1, 2, 3, and 4. And then your independent practice down here, students, is plot the points x, y, generate in part A, and sketch a graph of the parametric equations for t greater than or equal to 0. Describe the orientation of the curve. So for our guided, we're going to fill out this table for this situation here. So to do that, here would be your fill in here, 0, 0, 2, 1, 1, 1. So your B down here is for our x and y. This will be x, and then this will be y. And then for t, we fill in our t there for these values of t. Here's our table. And then we're going to use that to plot. This is for you to plot. And then sketch a graph. You can sketch it and describe the orientation of the curve, okay? Onward. Note that the graph shown, we go back to that graph again, does not define y as a function of x. It's not a function of x. So this points out one benefit of parametric equations. They can be used to represent graphs that are more general than graphs of functions. Oh, okay. Two different sets of equations can have the same graph. For example, the set of parametric equations x equals 4t squared minus 4 and y equals t -1 less than or equal to t less than or equal to 3 over 2. So it could describe that. Has the same graph as the set given in example 1. This would be that here. However, by comparing the values of t, you can see that this second graph is traced out more rapidly, considering t as time, than the first graph. So in applications, different parametric representations can be used to represent various speeds at which objects travel along a given path. So we can change the graph to describe the rate of change within a certain parametric equation. Using a graphing calculator in parametric mode, using graphing calculator to graph the curves represented by the parametric equations. Using the graph and vertical line test for which curve is the y a function of x. So here we have, use a graphing calculator to graph the curves represented by the parametric equation. So x equals t squared, y equals t cubed. So begin by setting graphing utility to parametric mode. When choosing a viewing window, you must set not only min and max values of x and y, but also min and max values of t. A. Enter the parametric equations for x and y as shown. So here's the x and y here. X is t squared, y is t cubed. Use the viewing window shown. So when you do that, let's make sure that you set your viewing window here. You have a y max 5, y scaling of 1, and etc. here. students. So go into your window parameters and make sure it's set like that. And then you get this curve here when you have from these two equations here. Here would be your curve y equals t cubed, and then x equals t squared. Okay. From the graph, you can see that y is not a function of x. It would not be a function of x here. Okay, our next one here, b, x equals t, then y equals t cubed. So enter the parametric equations for x and y. Here's your t. This is in our parametric equation menu for graphing, t and t cubed. Use the viewing window shown. So here's our viewing window parameters here. Y max 70, y scaling is 10. So from the graph, you can see that y is a function of x. Where's our graph at? Here's our graph. So here's our graph here. From the graph, you can see that y would be a function of x. Let's try another one. X equals t squared, y equals t. So enter the parametric equations like this, t squared and then t. And use the viewing window. So again, we got a different viewing parameters here. Y max 3, y scaling is 1, y min, and then x scaling, x max, and then x min. T step will be 0.1. T max is 4, then T min will be -4. So with that kind of viewing window, the curve is shown. Curve is shown from the from this graph here. You can see that y is not a function of x again because it will not pass the vertical line test. So y is not a function of x. So let's try one. Consider these two parametric equations. Radical t and then y equals 2 minus t. C. Use a graphing utility to graph the curve represented by the parametric equations. And then down here for your independent practice, find a rectangular equation by eliminating the parameter. Sketch this graph. How does the graph differ from those in parts B and C? So for these two parametric equations up here, this would be your graph here for these two situations here. Use a graphing calculator. That would be what your graph should look like. And then for those other students, I'm going to let you do that. And that is 9.4 part 1, pre-calculus math. Email me at animatedpowerpointmathvideo@aol.com for course materials, etc. Thank you.